Okay, hello everyone. A pleasure to be able to join you today. I'm going to focus on soil structure interaction and work very closely near where the structure is as a complement to these very large scale studies that we have been listening to so far with, ground motion propagating from the source and so forth. So you might know that most of my contributions in this area have been made available in the peer code OpenSeas in the form of soil models for nonlinear plasticity, incremental plasticity response in 3D and 2D, and in the form of models built specifically for liquefaction, these so-called pressure-dependent models, and in the form of a coupled finite element formulation, which is the so-called a version of the UP formulation, so that finite elements can study problems in liquefaction and do fully coupled buildup of pore pressure and change in the soil properties all the way to liquefaction and post-liquefaction. So in this particular presentation, like I mentioned, I will try to focus on soil structure interaction. And OpenSeas has provided a tremendous opportunity for researchers to exercise their geotechnical tools along with state-of-the-art structural elements, beam column elements and others that have been included in OpenSeas by other researchers. So it's really been a tremendous opportunity allowing us to use the OpenSeas framework and do our geotechnical work and also look at structural response at the same time. And I might want to look at strains in soils in a few ranges. So let's say, for example, ranges where equivalent linear analysis often gives very good results. Let's call that small strains. And then let's look at strains that maybe go up to 1% and call those large strains. And again, some people get reasonable results from equivalent linear analysis up to this range of shear strain. And then let's say that there are very large strains as those strains that occurred during liquefaction in slopes and such. Let's say that is of the order of 10%. And then I also found that there are scenarios of very, very large strains. And so we're talking about scenarios of the orders of 100% and more. And for each one of these range of strains, there are challenges and there are engineering ways to attempt to deal with these strains and still obtain a reasonable result. In the coming slides, I want to show examples of 3D response, 3D ground response under a variety of scenarios. So in an attempt to illustrate some of the things that we have learned from the analysis and some of the things that we have faced in our attempt to get this work done. So like I said, everything coming up will be about 3D simulations. And as you see here, we'll look in the beginning at a very large ground mesh with a rigid embedded structure, like something for a nuclear power plant containment structure in the middle. Then we'll look at large pile groups and interaction with the ground, simulating each pile in the pile group and the entire response of the ground structure system. Then we'll look at a study that we conducted a few years ago on three-dimensional response of, again, an entire bridge system. And then we will see how we attempted to adapt 3D modeling to look at wharf structures in seaports supported on piles, and to look at also entire bridge ground systems, as you see down here on this slide. So let's look at the nuclear power plant and the site response. So as you see here, this is a large ground mesh, about 60 meters in depth and 400 meters by 3/4 of a kilometer in dimensions. And the containment structure, as you see here, is embedded in the ground, 22 meters depth by 45 meters width. And actually, these dimensions very much are taken from dimensions of a very early study that was conducted by Seed and Idris, again, at the response of an embedded structure. And so we followed from there, and we worked in 3D to look at this problem. So this is just a schematic of the shear strain versus shear stress. And in this particular exercise, shear strains reached a high of 0.3%. So as you see here, we conducted nonlinear analysis, and we also conducted equivalent linear analysis using this G over G max curve and this damping curve that you see here. And like I said, peak shear strains were of the order of 0.3%. So we conducted equivalent linear, and we conducted nonlinear, and we compared the outcomes. So we look first at the ground response. Very far away from the structure, we essentially get the free field response that you would get from a program like Shake if you're doing equivalent linear analysis, or if you're doing a shear beam, a nonlinear shear beam of some kind. This is the response you would get far away from the structure. And as you see here, this is at ground surface, and this is at the level of the base of the structure. The responses are not that different. This is here weaker shaking. This scale of 4 is the input motion scaled up by a factor of 4 times, so it's much stronger shaking. And we see we lose the amplification that often is seen when the shaking levels are low, and we see a resonance. So here the resonance is muted and the frequency is spread out. But the main difference between nonlinear, fully nonlinear, and equivalent linear, as you see here, is that the equivalent linear just has much less high frequency. This is here equivalent linear, this is nonlinear, and you see much less high frequency. Peak accelerations are pretty good, and equivalent linear did well, except for the high frequency that's in the free field. Now, when we go to the structure, we find that the structure itself, because of its embedment at 22 meters depth, actually is quite insensitive to what happens in the upper 20 meters. It's fairly rigid compared with the surrounding soil. So it inherently filters all the high frequency out. It's moving kind of like a rigid body primarily. And as you see here, compared to the free field, which is in black, and the gray of the structural response is much less in amplitude, because this amplitude at the ground surface is very similar to the amplitude at depth at the base of the structure. And the high frequency is gone compared with the free field, which actually makes you even think, well, in that case, since the equivalent linear didn't reproduce the high frequency, maybe we get a good answer from equivalent linear. And the answer is absolutely yes. Since the structure already is filtering the high frequency, so as you see here, if you compare nonlinear to equivalent linear in this case, you see that the responses are very, very good under low levels of shaking. And even under the high level of shaking, 4 times the shaking level, the response is not bad. And the high frequency is absent anyway, because of the filtering effect that resulted from the presence of this rigid structure deeply embedded, as you see in this case. In terms of earth pressure, this has been something that people have also been always concerned about. What are the earth pressures? What is the distribution of earth pressure on the sides of the structure and on the base of the structure? And what you see here is that during an excursion, when the motion is in this direction and the structure is deforming in this configuration, the soil on the left is weaker and it's pushing on the structure, as you see here. And it turns out that it's pushing in the form of this configuration. It's not a triangular distribution at all, as some people postulate in terms of thinking, oh, this is an earth pressure Mononobe Okabe type problem. This is on the side that it's pushing, and on the side that is resisting, you see that the resistance is in the form of triangular. And because of the rotation of the structure a little bit here, the resistance is very high at the base, and gets even higher when the soil is pressure dependent And so it gets more confinement and becomes stronger as it's trying to resist. Okay, a very similar problem to that is the problem of large pile groups. As you see here for this bridge, to allow enough clearance for ship for navigation, the pile group and the pier in the center of the bridge is very high, much higher than the ones on the ends of the bridge. And if you look here, you'll see that in this middle of the bridge zone, the clearance is 27 meters. And then you have 14 meters between the pile cap at the level of the water in the channel, and the mud line is 14 meters, and then the piles are embedded for 16 meters into the ground. So you see that the inertial load coming from the deck of the bridge here in the transverse direction doesn't only apply lateral loads like you see by this arrow, but it applies tremendous moment because of this huge moment arm from the deck of the bridge to the pile cap. And so in this scenario, looking at a model of the entire pile group this way and the close interaction between the piles, the spacing between the piles is quite close in this case, and consequently the piles are interacting quite heavily. If we do a pushover analysis, what you will see in addition to the moments is that the axial loading is in certain ways dominant because of the moment that is accompanying the lateral load coming from inertia of the deck. And you see that compared to a single pile, the load carried by a single pile, if there was a single pile on its own that carries the load at 900 kilonewton, first of all, under own weight of the bridge, the outer piles carry a lot more than the inner piles. This is a half a mesh here, so this is an axis of symmetry. The pile group is double the size here. And so here is the static weight of the bridge alone. Here is the consequence when there is also the lateral load applied. And you see that the outer pile carries 5 times what the single pile carries, and the inner piles carry very little of the load compared with the outer piles and the corner pile in particular, because there is more soil around it outside that it can transfer load towards. Also, in the case where now this is the force only, lateral force only applied, if we apply the force and the moment, you see that the numbers become crazy in compression. And also these red numbers here are in tension on the back side of the pile group. And you see these huge numbers, 8 times the 900 kilonewton are happening in tension. And there is a very good chance that, of course, the pile to pile cap connection will not carry this kind of load, and there will be separations if a scenario like this takes place. And it was an opportunity for us to see that in addition to our interest in shear loading and the dominance of shear waves as the earthquake waves arrive close to ground surface, there is a lot of other characteristics that are happening in 3D and all kinds of loads on the ground that necessitate a much closer look at 3-dimensional response and models that reproduce these 3-dimensional response. Okay, so looking at a situation of a wharf on piles, which is the dominant way of constructing wharfs in the United States in ports. So this is here the container ship, here are the cranes, and they are supported on this wharf on hundreds, if not thousands of piles. And you see here, this is the deck of the wharf, and here are 6 rows of piles. And then this repeats over and over along the length of the wharf, which was a scenario that led us to think that because of symmetry, if we take a 3-dimensional slice, what is shown on red here, and we study this slice with as many elements as we can use, we can get a very good answer, a very good representation about the transverse response of this wharf, which is the important response because this is where the slope is that the wharf is facing, like you see here with this slice being our 3-dimensional model with appropriate boundary conditions on both sides because of symmetry. And with this logic, looking at the response, you see here that the deformed configuration, this is just an illustration of how the deformed configuration of the ground changes dramatically when you do the study with the piles in the slope. When you do the study without piles in the slope, which is what is shown here on the right, the deformed configuration of the slope is very, very different from what you get when the piles are there. So there were suggestions that we do a two-dimensional analysis of a slope and then take the deformed configuration and apply it here. But as you see, that doesn't work. You really need to do the study with the piles in the ground to get something realistic that you can compare with. Okay, so in addition to the lateral deformation, which you can see that it's not very different from the front to the back, whereas some people were thinking that these back piles here, because of that short clearance, if everything has to move the same distance, then these piles in the back would break much more easily because they are short compared with these long piles that would flex. But that didn't turn out to be the case because of the deformation of the ground around them, as you see here, moving the back and the front together. And in the end, what also appeared to be very, very important to pay attention to, because all the piles are connected rigidly to the pile cap, is that very, very significant axial loads get generated in the front, middle, and back piles because of settlement of the slope near the land side, heave of the slope near the water side, and the difference in the types of soils in which the piles are embedded and the depth of embedment, since they're all in the end connected to that rigid top, as you see here. So that was, again, another scenario showing characteristics of three-dimensional response that we don't see or need to be worried about if we are looking at ground response on its own. Another study that was done to look at the response of our entire bridge ground system, as you see here, and try to reproduce the characteristics that we observe after earthquakes. Like I mentioned, we are building on fiber elements and advanced structural elements. So not only is the soil nonlinear, but also the ground is nonlinear. And as you see here in plan view, after the shaking, the approach ramps settle sideways, they spread out sideways. The land around the bridge moves down slope, and the ground inside in the middle here heaves because of the soil moving from both sides into the middle of the canyon. And then you see the deformed configuration of the bridge and the displaced configuration of the different piles. And it sends you the message of that if someone is trying to study one slope at a time or trying to study one pier at a time, they really need to make lots of assumptions and be very careful and cognizant of this overall picture of deformations. So more recently, we started also looking at liquefaction for bridges, and we are modeling actual bridges as best as we can with actual ground profiles from the borings available to us. And you see first that, again, when you start looking at long distances, the layers are not continuous necessarily. And again, using that logic of the slice on a bridge as an approximation, it's not as good as an approximation as it was for the wharf, because the wharf was much wider. But nevertheless, we could still learn a lot from this three-dimensional model. And what we learned, for instance, is that when the shaking was done with a motion that had a pulse, like the Rinaldi motion, a motion that had a fling, if you will, a near field, the so-called near field motion, not only did we get deformation at the left slope and the right slope, but we also got entire lurching of the whole upper layer supported on the liquefiable layer here as permanent deformation of the entire ground. So in addition to the deformation from the slopes, you also potentially get just lurching of the ground all around that has to be taken into account, because it adds to the trouble that happens here on the left side deformation of the slope. And since time is tight, maybe I can use this slide here and mention to you that on this side is because of deformation of the slope. On this side, there is deformation of the slope from the middle here, the base, but there is also, because the bridge moves towards the right side, there is a double action here on the piles, and this motion here is a consequence of the motion on the left side. Interestingly, in the slope,
we've got to wrap up. Yeah.
Yes, sure. Interestingly, in the middle of the slope, because the soil doesn't move much in the middle, the motion of the soil downslope is here on the left and here on the right, and the zone in the middle doesn't move much, but the deck itself moves because it's pushed by the left slope. And you see that these systems in the middle also face trouble, not because of the trouble to the pile foundation in the middle of the canyon, but actually because of motion of the deck pushed by the side slope. In a narrow canyon, you see that deformations from the left and right slopes interact. And in this particular scenario, we ran the one slope on its own, and it gave us deformations of 5 meters. When we ran it with the 3-dimensional configuration that you see here, the deformation was only about 70 centimeters. So looking at systems often just is really the only way to do the study. Okay, quickly, the tools that I have used are all available, and they're all OpenSeas based at soilquake.net if you would like to use some of these tools. And more recently, we started trying to put our UCSD soil models also in other codes such as FLAC and LS-DYNA and Diana and Abacus. So there are versions of those available now if you'd like to use them in these other codes. Also, with the emphasis on downhole arrays as a way to calibrate models, there is a page that has the low tongue downhole data and the wildlife refuge data available that you can download and use for your analysis and calibration. And finally, I wanted to touch on large deformations and recent work that is ongoing now with Professor Chen from UCSD, who is an expert in mesh-free methods. And as you see here, working with him and working with softening models, which again, many soils exhibit in the response, we started doing some work that will materialize soon into the last slide. Oops, well, it overshot.
Okay.
Will materialize into a mesh-free public domain MATLAB code. So that should be ready in a few months. It will be published by peer. And then this is additional ongoing work in the mesh-free method. Thank you very much.
Wonderful. Thank you. Comprehensive.